Hello, everyone, and welcome to PyData Global 2025. We're excited to have you join us. Feel free to use the chat to connect with fellow attendees and share your thoughts during the session. If you have any questions, please post them in the Q&A tab and we'll address them at the end of the session. Now, it's my absolute pleasure to introduce Clinton Oyogo-David. He'll be presenting a talk entitled Engineering Large-scale Geospatial Rasters with xarray and dask, an exciting session we've all been looking forward to. Let's give a warm virtual welcome to Clinton.
All right. Thanks a lot, Peyton, for the introduction, and welcome everyone to this session. Swahili, we say karibu. As been introduced, my name is Clinton Oyogo-David, a data scientist at Oxford Policy Management, where I work as a consultant. But prior to joining Oxford Policy Management, I worked at World Agroforestry Center, currently known as C4ACRAF, the Spatial Data Science and Applied Learning Lab. And that's where I got to know a thing or two about GIS. My background is in statistics. Yeah. So this is all to say that I am not a data engineer per se, neither am I geospatial expert such. I'm just a data scientist who, uses the little knowledge that I know about GIS to deliver data analytic components for various projects that I work in. So that's it for my introduction. I'll now straight away get to the talk today, where I'll be talking about engineering large-scale geospatial rasters with xarray and dask. Some agenda for talk will be taking us through some definitions of terms, talk about spatial data, give us background of the problem that led me to develop this workflow, and then take us through the solution architecture, the critical design decisions that I had to go through, born out of the journey of debugging, fixing issues, until finally I developed the workflow that worked as I had desired. And then I'll talk about the best practices summary, and then finish it with further reading, some links to some materials that will be helpful. So that's it for the agenda. So let's talk about a bit of definitions. Geospatial data is spatially referenced data sets, typically vector or raster. So vector, this refers to points, lines, and polygons. This could be administrative boundaries, but we're going to refer to zones throughout this talk. Vector data can also represent roads, rivers, and buildings and such stuff. And then CRS stands for Coordinate Reference System. And this is how coordinates are mapped to the Earth's surface. And by resolution, this refers to the size of each pixel. It can be 100 meter by 100 meter. I'll talk more about this when I'll be talking about rasters. And small area estimation, this is a statistical technique used to produce estimates for small geographic areas or domains when direct estimates from surveys are unreliable due to small sample sizes. A little bit of deep dive into what a raster is. So a raster is a two-dimension matrix where each cell has geographic coordinates and a value. This can be precipitation, temperature, population density, land cover, and other phenomena that can be represented in a raster format. And it also comes with metadata such as the CRS, the resolution, extent, and other metadata. As you can see, if you have your raster, it can be representing population density, then each cell will be representing the number of people in a given cell or square of a given resolution. Could be 100 meter by 100 meter, could be 1 kilometer by 1 kilometer resolution. Yeah, so that's it. for definition of terms that I'll be using all through this presentation. Spatial data is gaining increasing attention as an unconventional data source for use in socioeconomic research because of its consistency, timeliness, scalability, and of course for the fact that it's usually available freely. Not all of it, but most of it is available freely. And so researchers are using satellite data to estimate poverty levels, analyze urbanization trends, assess agricultural productivity, and a myriad other use cases. But it comes with challenges. While satellite data has gained popularity, working with spatial data often presents challenges. One, it's not structured in a tabular format. Therefore, it requires specialized processing techniques. And this requires you to know a little bit of GIS to be able to know how to process your geospatial data. And the other problem with geospatial data is that, especially the raster data, it can be extremely large in size, hence necessitating advanced methods for efficient processing. Let me give it a bit of background on how I got to developing the pipeline. As part of a small area estimation workflow, we needed to extract zonal statistics from geospatial data for use in modeling poverty estimates at granular levels. And so we had to get data from various sources, harmonize this data, largely raster files, and then extract zonal statistics at the lowest administrative level. This was administrative level 3 for most countries, but for some it was administrative level 2. While this was feasible for Bangladesh, one of the project countries, we quickly realized that the workflow could not work for other project countries due to their large sizes. And as a result, large raster datasets. The initial workflow was in R, but obviously, as most of us, I guess, we know, working with R, there's a level beyond which it becomes hard. And so that's when I had to switch to using Python for this workflow. For instance, we worked with 6 population, actually it was 7 population density rasters from Meta. These were obtained from Humanitarian Data Exchange, and their sizes varied significantly based on country sizes. So this ranged from as low as 500 MBs to 20 GB per file. So as you can see, we are talking about 20 GB file, 7 of them in 8 countries. That's quite some big data. So processing such files alongside additional 20 other rasters for other geospatial covariates posed significant computational challenge. And this is what led me to investigate ways of processing huge raster files within limited resources. Solution architecture, one of the components of these pipelines is working with xarrays. Why xarrays? Xarrays provide n-dimensional labeled arrays with built-in geospatial awareness. So it comes with labeled dimension, which means you can work with coordinates rather than working with indices. It gives you access to lazy evaluation. So what this means is that you do not necessarily have to load your data into the memory. You only load what you need and when you need to do any computation. And the other good thing about xarray is that it integrates seamlessly with dask, which is a Python library used for parallel processing. Now, unlike traditional NumPy arrays, xarrays come with metadata, or rather the difference between NumPy arrays and xarrays is that xarrays come with metadata, and so that means we can geospatial data can be represented, and you can say, extract a given section of your data using coordinates, and of course you now understand the resolution of your data, the CRS, and all the metadata that comes with geospatial data. So that's one major difference between xarrays and the traditional NumPy arrays. The other component of the architecture is dask, which allows you to work with limits beyond the limits of your machine's RAM. So with dask, you can run tasks concurrently across multiple cores for faster, more efficient computation. And it scales seamlessly to distributed clusters, making it possible to handle massive terabyte scales of data. As you can see, this is how you do a configuration of a local dask client. And as part of the process of developing this workflow, I had to go through a process of making choices and critical decisions, based on the experience of, hitting a dead end, having to think on how to navigate some blockers that I got along the way. So the first decision I had to make, this decision I had to make, is around how to classify the data sets. So one critical step in the workflow was to harmonize the data, given that it came from different sources. So I had to clip some files into the region of interest, resample to ensure that they match in terms of resolution and the CRS. And so to do that, I put the data in 3 folders. So the first folder contained data that needed downsampling. So this is data that had high resolution, so I had to downsample that. Second folder contained data that had, very low resolution, so I had to upsample that. And the last folder had data or raster file that were already aligned. So those ones did not need any form of transformation in terms of resolution and CRS. The other critical decision is about chunking. So chunking directly impacts memory per worker, the number of parallel tasks, and the computational efficiency of your workflow. For instance, one of the rasters that I was working with yielded 260 chunk blocks, cut in 1024 by 1024 pixels each. And each of these chunk block was, in terms of size, was about 4 MB in terms of float 32 data. And if you go through the xarray documentation, you'll see this flag that, and actually the task as well, that too many chunks leads to massive task graph. I'll talk about task graph in the next slides. And then it also impacts scheduler becomes a bottleneck, and it takes more time to manage tasks than processing. And on the other side as well, too large chunks will require more memory per worker. And the other thing about chunking is that you need to align your chunks when operating on multiple arrays. Chunks need to align. And so this came in at the point where I had to rasterize the polygons, which is the zones, to then chunk and create an ID for each zone, and then now calculate the zonal statistics of each zone, of course, for each chunk, and then sum it up to each zone. And so at some point, I got a challenge because now the zones were split up in 512 by 512. And the raster chunks, I had split them by 1024 by 1024 pixels. And so they did not align, and this was a major challenge. So take note of chunk alignment when you're working with your chunks or data that's split up in chunks. So the other critical decision that I had to make is take note that the vector data, which is now the polygons, the administrative zones, often comes, packaged as shape files or JSON files or shape files. And so for my workflow that I was working with chunks and, raster data, I had to rasterize the administrative zones. As you can see the demonstration of this image here, this is what happens when you rasterize vector polygons. The other critical decision and important thing to take note of is you really need to understand how dask graph work and what impacts them. So a dask graph is Dask's internal presentation of your computation as a directed cyclic graph. So for my pipeline, the task graph in my pipeline had, remember I split up my rasters in 1024 by 24, which for the size of the rasters I was working with yielded 260 tasks, which is essentially 260 chunks. Now, what I'm highlighting here are just functions within my workflow. So this is just a graph just showing the dependencies between different functions and the outputs from different functions and how they are passed on to other functions and methods within the workflow. And so for each layer, which is the major steps in my workflow, you would need to process about 260 chunks, which translates to task graphs. And so in total, in the 4 layers, this was amounting to about 781 tasks. So if I were to split up my raster in 512 by 512 blocks, as you can tell clearly, that means that I'll have more chunks, which translates to more tasks. And so the task graph will grow in size. And this can be a major blocker in your pipeline when you're working with task. The other critical decision is about reprojection. Before I discovered WAP VRT, reprojection was really a pain point, even with chunking. It didn't work. So I had to try and find ways to navigate this. And that's why I arrived at working with WAP VRTs. So the issue was potentially caused by chunk misalignment across CRS transformations, which led to having to swap chunks which were overlapping. And so a little bit of definition of what WAP VRT is. This is a virtual raster format that performs on-demand windowed reprojection. So how it works is that it reads and writes data in chunks or directly between files. This it does by creating a virtual file. Think of it like a database view with the desired CRS and resolution. So when reading the chunks for further processing, we're actually reading from the reprojected raster, which, as you will see in my workflow, calling it, not calling it, but is the VRT grid. The good thing to take note about this WAP VRT is that you can also use command line tools like GDAL to reproject your files in a scenario where perhaps you don't want to include this step in your workflow. You can just do your reprojection on the command line and then now work with the reprojected raster files. The other critical decision with this workflow is task configuration. Now, depending on your resources, choosing the right configuration determines how fast your pipeline executes, or even whether it executes. For my case, more workers with less threads work best. And of course, working within the available RAM. And one thing to consider, or rather the major thing to consider, is that if your operations are CPU bound, then you'll need more workers. If they are IO bound, involves writing to and from the disk and between networks, then you will need more threads as well. So this is just a screenshot from my workflow. And the beauty with dask and xarray is that I was able to process 20 GB raster with about, so this translates to about, yeah, with just limited resources, was able to do that. So, so xarray and dask is really a game changer. So to finish off, this is the summary of my pipeline. As you can see, you start with setting up the dask client, and then you lazily load your rasters, which then are reprojected using the WAP VRT reprojection. And then now the reprojected raster, which is chunked, is then passed to again rasterize the vector polygons and to align to ensure that the vector polygons are chunked in alignment with the raster chunks. And then now this is now passed on to the last workflow, the last step in the workflow, which is to compute the zonal statistics. As you can see, each worker assigned about 5 GB of RAM, processed, it gets allocated a number of chunks and then works within the limits of the memory allocated. And yeah, my workflow worked fine with this setup. So as I finish off, the key lessons from experience is that chunking is fundamental. So you need to choose the right balance, the right size of chunk balances parallelism and overhead. And the other critical thing about chunking is that alignment across arrays is important. Lazy evaluation is powerful, so build the entire pipeline before you execute. And then use single compute for complex workflows. So this compute is a dask function or method. And then WAP VRT enables lazy reprojection. And finally, the major thing about my experience is that, well, as you go through, building your pipeline, each error teaches you something. And as you go through the debugging experience, it deepens your understanding of different concepts. And of course, the best approach is to build incrementally. Yeah, so for further reading, you can check the xarray documentation, view xarray, dask, and GDAL virtual format, VRT. So thank you. If you need to get in touch, you can reach me through my email or we can connect through LinkedIn. Thank you. And that's it. I don't know if there are any questions or comments.
I think we're good to go. But thank you all so much for joining us today. And thank you, Clinton, for your time. If you'd like to continue the discussion, head over to our Discord, and a recording of the session will be available shortly for rewatching. And for those interested in more casual conversations, the lounge is open in the reception for small group discussions. Thank you for coming again. I hope you have a good rest of your day.
Thank you. Bye.